The Mediterranean Sea, an ancient cradle of civilization, has long been perceived as a relatively stable expanse, its shores graced by millennia of human history. Its azure waters and serene coastlines evoke images of timeless beauty and enduring tranquility. Yet, beneath this familiar surface, deep within the Earth's crust, formidable forces are constantly at work, reshaping the very foundations of the region. Recent findings suggest a geological anomaly of profound significance may be unfolding, challenging our understanding of this iconic basin and hinting at a restless future. Geologically, the Mediterranean is a complex mosaic, a battleground where the African and Eurasian tectonic plates converge. This slow-motion collision, spanning millions of years, has sculpted its dramatic mountain ranges, deep trenches, and active volcanic arcs. It's a region defined by subduction, where one plate dives beneath another, melting as it descends into the Earth's mantle. This process fuels the very heart of the Mediterranean's geological activity, creating the conditions for magma generation and, occasionally, powerful eruptions that remind us of Earth's raw power. Deep below, far from human sight, enormous reservoirs of molten rock, magma chambers, accumulate. These subterranean cauldrons are the engines of volcanism, pressurizing and storing magma before it makes its journey to the surface. For decades, geophysicists have mapped these hidden structures, often associated with known volcanoes like Stromboli or Etna. But what if a significant magma chamber, one of colossal scale, existed largely undetected, its presence only revealed by its profound and unexpected behavior? This question now lies at the heart of a new investigative inquiry. The first subtle clues emerged not from dramatic eruptions, but from painstaking analysis of satellite data. Researchers tracking tiny movements in the Earth's surface using high-precision GPS receivers and satellite interferometry, known as INSAR, began detecting unusual patterns. For years, regional subsidence and uplift were largely attributed to known tectonic processes. However, a specific area, predominantly in the central Mediterranean, started showing a consistent and accelerating downward movement, a subtle sinking of the crust that defied easy explanation by existing models. Focus soon shifted to the Tyrrhenian Sea, a deep oceanic basin situated between the Italian peninsula, Sicily, and Sardinia. This region is known for its active volcanism, including the Aeolian Islands and numerous submarine volcanoes. Historically, volcanic activity here has been well documented. However, Dr. Elena Rossi, a geophysicist at the National Institute of Geophysics and Volcanology (INGV), noted that the observed subsidence was far too widespread and prolonged to be solely attributed to post-eruptive relaxation or local hydrothermal activity. It pointed to something far deeper and more extensive. Further corroborating evidence emerged from gravity measurements. Gravity, a subtle yet powerful force, varies across the Earth's surface depending on the density of the underlying rock. A research team led by Professor Marco Bianchi from the University of Bologna began detecting localized decreases in gravitational pull over the Tyrrhenian Sea. A decrease in gravity can indicate a reduction in mass beneath the surface. This finding, published in a Geophysical Research Letters, suggested that a significant volume of material, likely molten rock, was either evacuating or becoming less dense in the Earth's crust. Simultaneously, seismic monitoring stations recorded an increase in microseismicity, small, frequent earthquakes, emanating from depths greater than typically associated with surface volcanic activity. These tremors, though minor in magnitude, provided crucial acoustic signatures. Dr. Sophia Chen, a seismologist at the German Research Center for Geosciences, explained that these seismic signals were consistent with the fracturing of rock as a large subsurface void underwent pressure changes. It was as if the Earth itself was groaning under an immense, unseen stress. Connecting these disparate observations, surface subsidence, gravity anomalies, and deep microseismicity, a groundbreaking hypothesis began to form among the international scientific community. A hidden, deep-seated magma chamber beneath the central Mediterranean was not filling, but actively draining. This idea, initially met with skepticism due to its scale and the absence of a major eruption, gained traction as more data aligned. The question then shifted from "is it happening" to "how and why?" To visualize what lay beneath, researchers turned to seismic tomography, a technique akin to a medical CT scan for the Earth. By analyzing how seismic waves from earthquakes travel through the crust, scientists can create 3D images of subsurface structures. Dr. Kenji Tanaka's team at the University of Tokyo applied advanced tomographic methods to the Tyrrhenian data. Their findings, published in Nature Geoscience, revealed a large, low-velocity zone consistent with a significant magma body, approximately 15 to 25 kilometers deep, showing signs of reduced volume and increased fracturing around its periphery. As the underlying magma chamber slowly deflates, the crust above it loses support. This gravitational collapse manifests not as a sudden cataclysm, but as a gradual sinking and fracturing of the overlying rock. These are the cracks referenced in the initial observations: surface fissures, seabed fault lines, and microfractures within the bedrock. Marine surveys in specific areas of the Tyrrhenian Sea have documented new, subtle fissures on the seafloor, some extending for several kilometers, indicating significant stresses on the crust. But how does a colossal magma chamber drain without an explosive eruption? Volcanologists propose several mechanisms. One is lateral migration, where magma flows horizontally through conduits and dike systems into adjacent, shallower chambers or existing fault lines. Another is deep drainage, where magma slowly seeps into deeper parts of the mantle, potentially through newly formed cracks or pre-existing weaknesses in the crust. This slow, almost imperceptible process explains the lack of immediate surface violence, yet its long-term effects could be equally profound. The real-time aspect of this phenomenon is crucial. While geological processes typically unfold over vast timescales, the observed rates of subsidence and magma evacuation are significant enough to be measured and tracked within a human lifespan. Dr. Ross's team, using continuously updated INSAR data, reported subsidence rates of up to 5 mm per year in the most affected areas. This may seem small, but accumulated over decades, it represents substantial crustal deformation. This isn't a snapshot, it's a dynamic, ongoing event. Understanding why this draining is occurring is perhaps the most challenging question. One leading theory, put forth by Professor Giovanni Russo, posits that ongoing subduction of the African plate beneath the Eurasian plate is not uniform. Localized tearing or detachment of the subducting slab could create pathways for magma to escape downwards or laterally. Another hypothesis suggests changes in mantle convection currents might be pulling magma away from the chamber. It is a complex interplay of forces, far beneath our feet, that dictates this subterranean ballet. Quantifying the amount of magma being drained is critical. While exact figures remain elusive, seismic tomography and gravity anomaly data allow for estimations. Dr. Tanaka's preliminary models suggest a magma volume equivalent to a cubic kilometer might have been evacuated from the chamber over the last 2 decades. To put that into perspective, it's roughly the volume of water held by a medium-sized lake. This is a substantial geological event, not just a minor fluctuation, and it underscores the power of the Earth's internal processes. One of the most concerning long-term implications of a draining magma chamber is the potential for caldera formation. A caldera is a large, basin-shaped depression formed when the roof of a magma chamber collapses after an eruption or, as in this case, after significant drainage. While there's no immediate threat, the persistent subsidence and fracturing over decades could lead to a gradual collapse, creating a new geological feature on the seafloor, potentially altering marine ecosystems and even triggering localized tsunamis. To contextualize the Tyrrhenian phenomenon, it's useful to compare its observed drainage rates with other well-documented cases globally. While not identical, some volcanoes, like Kilauea in Hawaii, have experienced periods of rapid magma withdrawal during flank eruptions. However, the Mediterranean situation involves a deeper, presumably non-eruptive drainage over a larger, diffuse area. This difference highlights the unique geodynamic setting and the challenges in predicting its evolution. Scientists emphasize that direct comparisons are difficult due to varying geological contexts. The continuous, albeit slow, subsidence over decades could eventually have tangible effects on the Mediterranean coastlines, particularly in low-lying areas and coastal infrastructure. While a few millimeters a year might seem negligible, it compounds. Over 50 years, areas could sink by 25 centimeters or more, increasing vulnerability to sea level rise and coastal erosion. Professor Bianchi noted, while the process is slow, the long-term cumulative effects could significantly impact coastal communities, especially those built on unstable sediments or close to sea level. Beyond the geological and human impact, the draining magma chamber could also have ecological repercussions. Changes in seafloor topography, altered hydrothermal venting, or even subtle changes in deep-sea currents could affect marine life. The creation of new cracks and faults could expose new mineral resources or, conversely, disrupt established ecosystems dependent on specific geological stability. Marine biologists are now collaborating with geophysicists to monitor any corresponding shifts in deep-sea biodiversity and ocean chemistry. As more data poured in from various international institutions, the initial skepticism surrounding the draining magma chamber hypothesis began to recede. While debates continue regarding the precise mechanisms and long-term trajectory, a general consensus has formed within the scientific community. A significant subsurface magma body in the central Mediterranean is undergoing a period of sustained mass loss, leading to measurable crustal deformation. This agreement highlights the power of collaborative, interdisciplinary scientific inquiry. While this phenomenon is specific to the Mediterranean, it contributes to a broader understanding of deep Earth processes globally. The Earth's interior is far from static, it is a dynamic system of convection, melting, and movement. Cases of magma chamber inflation and deflation are observed worldwide, but the scale and depth of this Mediterranean event offer new insights into less explored mechanisms. It prompts scientists to re-evaluate what we consider stable geological regions and to refine our models of crustal evolution. Assessing the risks associated with this draining magma chamber presents unique challenges. Unlike an active, erupting volcano, the threat is diffuse and long-term. There's no immediate eruption forecast, but rather a slow, persistent deformation. This requires different monitoring strategies and public awareness campaigns. Dr. Rossi emphasized, our challenge is to communicate a long-term, slow-motion risk that isn't immediately catastrophic, but has significant cumulative impacts. It demands a shift in our approach to natural hazard assessment. In response to these findings, an international consortium of geoscientists has intensified monitoring efforts. New seabed sensors, improved satellite tracking algorithms, and a denser network of onshore GPS stations are continuously feeding data into research centers. This real-time surveillance is crucial for tracking the rate of subsidence, identifying new fracturing zones, and detecting any changes in magma flow patterns. The goal is to build a comprehensive picture of the chamber's evolution, allowing for more accurate long-term predictions. While the core hypothesis of a draining magma chamber enjoys broad support, certain aspects remain subject to scientific debate. For instance, some researchers, like Dr. Lars Nielsen from the University of Copenhagen, propose that a portion of the observed subsidence could be attributed to deep-seated fluid withdrawal or localized compaction of sediments, rather than solely magma drainage. These diverging views are healthy within science, pushing for more robust evidence and refined models, ensuring that every angle of this complex phenomenon is thoroughly explored. The depth of the identified magma body, estimated between 15 to 25 kilometers, is also a significant factor. Such a deep chamber behaves differently from shallower ones, which are more directly linked to surface volcanism. This depth makes direct observation impossible and requires reliance on indirect geophysical methods. The interaction of the draining magma with the lower crust and mantle remains an area of intense research. Dr. Chen commented, understanding the deep interaction zones is key to predicting any future surface manifestations. A critical question is whether this drainage could be a precursor to a future eruption, perhaps in a new location, or if it represents a process of devolatilization and where magma becomes less volatile and moves deeper. Current evidence suggests the latter, or a lateral migration without eruption. While the possibility of future volcanism cannot be entirely ruled out in such a dynamic region, scientists emphasize that the observed changes are not indicative of an imminent catastrophic event. The process appears to be one of slow, deep redistribution rather than rapid ascent. The Mediterranean has a long and turbulent geological history, marked by episodes of intense volcanism, seismic upheaval, and dramatic landscape changes. From the collapse of the Minoan civilization possibly linked to the Thera eruption, to the ongoing activity of Etna and Stromboli, the region is no stranger to Earth's power. This new discovery adds another layer to that history, revealing a more intricate and constantly evolving subterranean landscape than previously understood. It's a reminder that even in seemingly stable times, the Earth is always in motion. The Tyrrhenian phenomenon might not be unique. Similar subtle subsidence patterns could be occurring elsewhere in the world, unnoticed due to less dense monitoring networks or different geological settings. This discovery encourages geoscientists to re-examine existing datasets from other tectonically active regions for similar subtle clues. If deep magma chamber drainage is a more widespread phenomenon than currently believed, it could significantly alter our understanding of crustal evolution and the global volcanic budget. The role of water in deep crustal processes is also under investigation. Seawater infiltrating through the newly formed cracks and fault lines could interact with the hot rock, potentially influencing fluid pressure and localizing stress, which in turn could exacerbate subsidence. Hydrothermal circulation, driven by this interaction, might also be changing, affecting marine ecosystems and potentially altering the chemistry of the deep-sea environment. This complex interplay between rock, magma, and water adds another dimension to the ongoing research. This discovery would not have been possible without significant advancements in satellite technology and computational modeling. High-resolution InSAR data, capable of detecting millimeter-scale ground deformation from space, and powerful supercomputers that can process vast quantities of seismic data, have revolutionized our ability to see into the Earth's interior. As technology continues to evolve, so too will our capacity to uncover Earth's hidden secrets, providing ever more detailed insights into its dynamic processes. While the scientific community is deeply engaged, communicating such complex, slow-burn phenomena to the public is vital. Ensuring that coastal communities understand the long-term implications of subsidence, without causing undue alarm, is a delicate balance. Educational initiatives and transparent data sharing are key. Professor Russo stated, "Public engagement is paramount. We must equip communities with knowledge, not fear, so they can adapt and prepare for geological changes that, while slow, are inexorable." In essence, the draining magma chamber in the Mediterranean can be seen as the Earth taking a deep, slow breath, a grand geological exhalation. It is a reminder that our planet is a living, breathing entity, constantly adjusting and rearranging its internal architecture. We are witnessing a fundamental process of planetary evolution, happening in our own time, forcing us to redefine what we consider stable and to embrace the dynamic nature of the world beneath our feet. Looking ahead, future research will focus on several key areas. Refining the precise geometry and depth of the magma chamber, improving models of mantle dynamics that might drive the drainage, and developing more sophisticated methods for predicting crustal deformation are top priorities. Furthermore, investigating the potential for induced seismicity related to these stress changes is crucial. Every new data point and every refined model brings scientists closer to a complete understanding of this profound Mediterranean mystery. The Mediterranean, often celebrated for its timeless beauty and rich history, now also stands as a testament to the Earth's relentless, silent pulse. The cracks forming, the land sinking, the subtle shifts in gravity, these are not signs of immediate disaster, but rather scientific breadcrumbs leading us deeper into the understanding of our planet's hidden mechanics. It's a testament to human curiosity and technological ingenuity that we are now able to detect and interpret these faint signals from the deep. This is not a story with a definitive end, but rather an ongoing narrative. The Earth does not operate on human timescales, and the processes currently unfolding beneath the Mediterranean will continue for decades, if not centuries. Scientists will remain vigilant, their instruments ever listening, their models ever refining. As we look out over the ancient waters, we are reminded that the most profound dramas often play out in silence, beneath the surface, shaping the world in ways we are only just beginning to comprehend.